So the first thing we're going to start with is looking at those formulas we've been working on over the past few lessons, except these problems are going to have different time measurements than what the function is originally written with. So the first one says a quantity with an initial value of 7,800 decays continuously at a rate of 7% per hour. So here is my key for my formula. When I see continuously, I know that we're going to use A of t equals p times e to the rt. Now, looking for those variables, my p-value is 7,800. E is just the number e. My r value, because I'm decaying, is negative 0.07. And my time we're going to look for in the problem. Now, one important thing here, we're looking at what time is measured in, and we'll have to pay attention to that throughout the rest of the unit. So time is in hours. So my original formula is going to look like this. So that's just plugging in those numbers. Now they want to know what's the quantity after 0.5 days. So half a day, we can't plug in a 0.5 because t is measured in hours. So in this case, half a day would be 12 hours. So I'm going to plug in a 12. So we have 7,800 times e to the negative 0.07 t. 12 plugged in for t there, right? And if I typed this in my calculator, we're not solving, we would just type that in. To the nearest 100, that would be 33,067 or 3,367.34. And it doesn't tell me what we're working with, so I'm just going to leave it like that. It's just a quantity. So let's look at the next one. A quantity with an initial value of 650 grows at a rate of 20% per week. What is the value of the quantity after 70 days to the nearest 100th? So this doesn't give me any information about compounding or anything like this. So this is just going to be our basic formula. So we're going to use A of t equals p times 1 plus r to the t. So that's our basic formula. Information given here, p is 650. We're growing at a rate of 20% per week. So that's r is 0.20 positive. And t is measured in weeks. So looking at this, we'll write our function first. 650 times, I could add this in my head, right? So I'm just going to do 1.20 to the t. Then reading the information we need to plug in, we want the quantity after 70 days. So looking at weeks, 70 days is 10 weeks, right? So that's 70 days, which is 10 weeks. So I'm going to plug that in. And if I take this in my calculator, that would give me 4,024.63. So let's look at our last one. And these are just kind of practice and also starting to get us to think about time a little more carefully. A quantity with an initial value of 290 grows exponentially at a rate such that the quantity doubles every 7 days. So this is doubling. So we're going to use our A of t equals p times 2 to the t over h. So h is like our half-life or our doubling time. We're still using that h variable there. So we're starting with 290. And then our doubling time is 7 days. So this is measured in days. Okay, so t is in days to go with the doubling time. So writing our function, Remember, we're always plugging in for that H first, so the T stays. Now it says, what is the value of the quantity after 54 hours? So we're measuring in days. If I do 54 divided by 24, 24 would be 1 day, right? We're going to see what fraction of a day 54 hours is, or what decimal in this case. So that gives me 2.25 days, which is what I'm going to plug in for T. So T equals 54 divided by 24, which is 2.25 days. So going to my formula now, 290 times 2 to the 2.25 over 7. We are nowhere near the doubling time with the 2.25, right? That's less than 7 days. So I'm not expecting this to double. I'm expecting it to be bigger, but not, double. So when I type this in, I get 362.37.